Today, we're diving into the fascinating world of forces. To start, could you clarify the fundamental difference between contact and non-contact forces, perhaps with some everyday examples?
Absolutely. Contact forces require two objects to physically touch. For instance, when you kick a football, your foot applies muscular force via contact. In contrast, non-contact forces, like magnetism or gravity, act across a distance. Think about how a magnet attracts iron filings without direct touch.
So, if I understand correctly, gravity pulling an apple to the ground is a non-contact force, while pushing a shopping cart uses contact force. Why is this distinction so crucial in physics?
Great question. Recognizing the type of force helps us predict and explain object behavior. For example, engineers designing maglev trains exploit non-contact magnetic forces to achieve frictionless, high-speed travel, while athletes rely on contact forces and friction for grip and control.
That's an interesting application. Before we move on, can you briefly mention any other non-contact forces besides gravity and magnetism?
Certainly. Electrostatic force is another key non-contact force. It's why a rubbed balloon can attract bits of paper. These forces underpin phenomena from lightning formation to the operation of photocopiers.
Building on our foundation, let's shift to friction. Many students know it slows things down, but could you explain how friction actually works, perhaps using a relatable analogy?
Think of friction like microscopic Velcro. When two surfaces touch, their tiny irregularities interlock, resisting motion. That's why a book pushed across a table eventually stops. The frictional force counters its movement.
Interesting. But friction isn't always bad, is it? For example, why is it easier to walk on rough surfaces than on smooth, wet floors?
Exactly, friction is essential for grip. On rough surfaces, higher friction between your shoes and the ground prevents slipping. On wet or smooth floors, reduced friction means less grip, making it easier to slip, as we see during rainy days or in bathrooms.
To deepen this, what happens if friction were completely absent, say, if you rolled a ball in a world without friction?
Without friction, the ball would never stop. It would keep moving indefinitely unless another force intervened. This scenario helps us understand why astronauts on the International Space Station, where friction is minimal, must use handrails to control their movement.
Let's transition to gravity and upthrust. We know gravity pulls objects down, but what determines whether something sinks or floats in water?
It's a tug-of-war between gravity and upthrust, the upward force exerted by a liquid. If upthrust equals or exceeds an object's weight, it floats. For example, pumice stone floats on water because its upthrust is greater than its weight, while a coin sinks because gravity dominates.
That makes sense. Can you illustrate this with a common experiment? Say with a plastic bottle?
Sure. When you immerse a plastic bottle in water, gravity pulls it down, but upthrust pushes it up. If you fill the bottle with air, it floats. Fill it with sand, and it sinks. This principle is why ships, despite their massive weight, float. They displace enough water to generate sufficient upthrust.
How do these forces change on other planets, for instance? Would the same bottle float differently on Mars?
Excellent scenario. Since Mars has lower gravity, the bottle's weight decreases, but upthrust depends on the liquid's density. So, the same object could float more easily on Mars if the liquid's properties are similar. This difference in gravitational force is also why astronauts feel lighter on the Moon.
As we wrap up, let's discuss how we actually measure forces and why this matters in real life. What tools are commonly used, and how do they function?
A spring balance is a classic tool for measuring force, especially weight. It contains a spring fixed at one end with a hook at the other. When you hang an object, the spring stretches. The extent of stretching is proportional to the applied force, which the scale displays in newtons.
Why do we use newtons as the SI unit of force?
The Newton honors Sir Isaac Newton, whose laws of motion underpin classical mechanics. 1 Newton is the force needed to accelerate a 1 kg mass by 1 meter per second squared. It standardizes measurements for scientists and engineers globally.
In practical terms, how does understanding forces help us in daily life or industry?
Knowledge of forces shapes everything from designing safer vehicles that optimize friction for braking to creating ergonomic tools that reduce muscular force needed to building structures that withstand wind and gravitational forces. Even amusement park rides are engineered with precise force calculations to ensure both thrill and safety.